go ahead and get started then. Again, good morning and thank you for joining us. I'm Kyle Hauger with Portland Metro and serve on the coordinating committee for OMUG alongside with Li Ming Wang of Portland State University and Garth Aponitis from DKF and Associates. And this is a team sport, so the three of us help plan and coordinate these meetings, and alongside help from Carol Richardson. We are happy to provide these forums for the modeling community within Oregon and frankly outside of Oregon as well. You can, let's see, go to the next slide there. Yeah, thanks, Carol. So quick overview of today's agenda. We've got a busy one today, but we'll start with kind of a couple of quick hits. We call them lightning talks from Brian Blanc of Metro and Matthew Titus from Sunstrand. And again, these will take anywhere from 5 to 7 minutes, just kind of quick hits of interesting, modeling related topics, not necessarily transportation modeling related, but forecasting and data analysis topics that are of interest, that may be of interest to this group. And then we'll get into kind of the more meatier, heavier kind of modeling topics in agenda items 3 through 5. Pretty ODOT heavy today, so thank you ODOT for raising your hands and completing our agenda today. And then at the end of the meeting, we'll cover announcements and some closing remarks. So yeah, I talked a little bit about lightning talks. These are relatively new. I believe we started this these lightning talks at our last meeting, and yeah, always looking for volunteers. Again, this group meets quarterly, and our next session will be late fall, and don't be surprised if you get tapped on the shoulder to talk about some cool work you're doing. Again, we try to get anywhere from 2 to 3 of these lightning talks to kind of kick off and get the juices flowing on these kind of longer meetings. So yeah, no time for question and answer kind of format on these things, but feel free to use the chat room. So that's kind of the ground rules for the lightning talks. They're pretty informal though. Next slide, Carol. So
I don't have another slide. We're ready to just launch in.
Okay. Well, there we go. I guess we're ready to go. And with that, I'll introduce Brian Blanc from Portland Metro. He's a senior modeler. I have the pleasure of working with him. He's relatively new to Metro. He was with Nelson Nygaard, I believe, in a past life, but we're sure happy to have him at Metro. And today he's going to give us a quick hit on FTA stops modeling. So with that, I will hand it out to Brian.
All right, thanks, Kyle. Go and verify they can hear me. I know I'm going to share my screen from my laptop and then speak through the mic.
Yeah, we can hear you good, Brian. Thanks.
Hi, everyone. Yeah, I'll talk to you a little bit about stops. Okay. So first, people aren't aware of what is stops. Stops stands for Simplified Trips on Project Software. The Federal Transit Administration released it originally in September 2013, and it's for transit ridership modeling, primarily for entering the capital improvement grant processes that the FTA administrates. It's on version 2.52 now, so it's been in operations for over 10 years. And yeah, as time goes on, it's becoming clear from FTA that's like there's very strong preference for modeling platform when you're going to enter the CIG process for a transit project. You can still use local models, but they're going to scrutinize it a lot more than they'll scrutinize stops. So why did FDA develop stops? A bunch of bullets I grabbed from one of their slide decks here. Focus on trips on the like major capital project being developed. One of their focuses was using readily available inputs and keeping it simple. So while we at Metro may feel our regional model might be more sophisticated and addressing like more ranges of behavior than stops will address. The goal is to keep it simple and to apply it. So basically, we compare apples to apples across a bunch of different agencies. And it definitely has a fixed guideway focus, but it does allow for detailed system-wide representation, fixed guideway focus, because usually that's what folks are applying for CIG grants for. Although there has recently been more of an emphasis in stops on kind of the partial fixed guideway mode, like bus rapid transit, essentially. So buses that have like some sort of fixed guideway characteristics. They calibrated against a bunch of existing rider survey data sets. And it is very plain on the outside, but there's a lot going on inside. Basically it's kind of emphasis on simplicity. Talking about like what are the minimum user inputs for stops. So you will need like existing and horizon near population employment for the project area, stops in its interior. Basically, one of the ways it gets around having any sort of other flow information is it uses the census transportation planning package to construct OD flows between zones. But it wants to scale those to your Metro's existing and horizon near population employment. It'll need auto travel time skims as well, because there's no internal representation of a network, but it does use zone to zone skims to like calculate what is the auto travel time and trade that off between what a transit travel time would be. It uses GTFS to define transit networks and therefore to calculate transit travel time, and uses existing route and stop level ridership for model calibration. The advanced user inputs that I have not used yet, but hope to use in the future, like the big one being onboard origin destination survey data, so that you can get more locally tuned flow information and the locally and modally tuned flow information of like how are people using transit from zone to zone. I definitely run into this in modeling work already of like the CTPP flows are not really representative of transit flows, but we're trying to like use those as a proxy. So an origin destination survey would be better, but those are really expensive. And then also special market trip generators you can put into the model as well, which I would like to do at some point. Like for example, in the Portland area, the airport, it's not well modeled by CTPP flows, for example. So it would be helpful to use some kind of special market trip generator. What I've been working on to date is I got an initial calibration for Parametrics, who's been kind of our primary stops consultant in the Portland Metro so far, and we're still working with them to train me. And I made changes to that model calibration to date to calibrate it for two of our big transit corridor projects in the Portland area, 82nd Avenue and TV Highway, that we're hoping to apply to CIG for in the next couple of years. I've developed a series of R scripts to ease kind of data input and output as I churn on various stops model runs. And so that's something I'd like to coordinate with people on in the future. And then, yeah, now I'm finalizing a model calibration and applying it to build transit network definitions. As an example of like issues I've found so far that have been challenging in stops.
All right, Brian, you have about 1 minute to go through just some highlights here.
Okay, sorry. All right, so I've had some issues with competition between parallel lines. I'll just say that. So Green Line and 82nd Avenue have been a challenge in stops, for example. The immediate next steps of what I'm working on, like a lot of documentation and then trying to get things out of my head and share it with other team members at Metro. So we have some redundancy in the team who can use stops. And then we're going to be recalibrating it again once we have some more data. As the post-pandemic new normal becomes more normal, this probably will be less necessary. But right now, as things are changing rapidly, it's helpful. And then this is something I'd like people's thoughts on in the chat is I'd like to develop a portal for like publishing a stops model calibration for other people to use. And so I was thinking something like maybe GitHub. And I'm sure there's other opportunities for coordination. So yeah, this is where I'm looking for this group. So I'll hand it off.
Awesome. Thank you, Brian. Lots of information there, lots of great information. I can see in your future, or maybe one of your teammates in the future, presenting on some application for sure of the stops model. And yeah, interesting stuff. Thank you for sharing, Brian. I appreciate it. Our next lightning talk comes from Matthew Titus. Matthew is a PhD and works with Sunstrand Technical Consulting, and this is an interesting use, I feel like, for our lightning talks. So when I say that, it's Matthew will give us a presentation on water supply forecasting. So not something that this group is traditionally well versed in, but interesting topic nonetheless, and definitely with his LiDAR focus and forecasting emphasis, I think it's pertinent to this group. So welcome, Matthew, and take it away.
All right, thank you, Kyle. Thanks everyone for letting me come talk. I'm very interested in what you all are doing, and there was this opportunity to talk a little bit about what I've been doing. And yeah, I heard LiDAR is enough to get people in the room excited, so I mean, we'll take it and run with it. So this is a project, my focus is on water supply, typically quality. Done a lot of water supply quality forecasting, but this is a project that was focused on water supply quantity. And it was done in conjunction with John Woodill out of Oregon State University, and a passel of folks from the NRCS, the Natural Resources Conservation Service. And so this is the title of our report. And we just wrapped that up a few months ago. So this is pretty new stuff. The NRCS has a dedicated effort that it's been doing for years and years of water supply forecasting, which every month they'll publish reports, and their reports will contain forecasts somewhere along the lines of how many 1,000 acre feet of water are going to flow past a certain stream gauge at some point in a watershed. And so on the right, you see the Tuolumne watershed here, and the Tuolumne River runs into the Hetch Hetchy Reservoir and then continues down to the Don Pedro Reservoir. And, this serves as a lot of communities, and knowing how much water is going to come down between April and July is really useful for planning. And so this is something that they've been using a few machine learning models for. I think Viper is still in use. There's this, it's just a simpler model, And recently they've come out with something called M4, which uses a much more advanced collection of models to do its prediction. But those are the machine learning efforts that have been done separately by the USDA. This project was pointed towards doing something else, and that's because further water supply forecasting, one of the major sources of data that they use is snow water equivalent that's gathered at stations like you see in the picture on the left. On the right, we have a marker for each of the stations that are in the Tuolumne Water Basin. These stations each have a snow pillow and one of these posts to read snow depth, and they use it to get an idea of how much water is actually in the watershed and latent, waiting to become runoff as things warm up. The difficulty here is that this is really spatially isolated. They just have a few points, but where they have these stations, they're getting daily data back. So you get these long time series that are rich, but there's just not that many of them throughout the watershed. So the Airborne Snow Observatories project, which came out of JPL, they've been doing flyovers for, around a decade now, and there's only a few per season. So you're kind of left with the opposite problem. Now we have a spatially complete, a very fine resolution, 50-meter resolution idea of how much snow water equivalent is in each of these pixels. And they do that by taking the LiDAR and they map out, this is the height of the mountain, and then they'll do their flyover in January and they'll say, this is the height of the snow, and the difference gives you an idea of the volume of the snow. They use a pretty advanced camera system to take hyperspectral images, and then they use that to get an idea of what the actual density of the snow is. So they get their SWE maps, but unfortunately there's only a few of them, and so it's difficult to train a model with such short time series. And so what we did was we created proxy data. We used the thrust of the project was to create a machine learning platform where we could take all of the data, say from the black checkers in this map, and we feed it into the model and train it to predict what the SWE would be at a given point. And that is based on the topography, the weather so far during that water year, and so on. That all gets used in training, and then we move to the white checkers, and we say, all right, given this topography and this Latin long and this weather history, how much snow should be there? And we find those models do pretty well. R-squared scores of around 0.7, so it captures a lot of the variance, and that's what we're using to extend our time series back in time. So now we can take historical weather and we can get an idea of what the snowpack would have looked like if we'd had a flyover back in 1970 or 1975. And so we get these long time series. And then finally, we take that proxy data and we throw it back into the M4 model and we see, does it help or does it hurt? And so unfortunately, it doesn't always help. So in this first basin that we were looking at, the Tuolumne, you actually get dinged a little bit, but the Tuolumne, just based on SNOWTEL data, it's already getting an R-squared score of close to 95. And so that's really high and tough to improve on. And in these basins that are a little bit more of a struggle, such as Blue River, the Dolores out in Colorado, we see that by adding in that ASO data, you can get some pretty sizable boosts in your R-squared scores, which are shown here. I've labeled them with the 2 and the 3. So out in the Dolores, if you add in your proxy ASO time series, temperature and precipitation, and you train a model, you can get a boost of about 0.2 to your overall R-squared score. So that's what we did. Thank you so much for your time.
Okay. Cool project, Matthew. Thank you so much for sharing. I'm glad you found our group. And I think it fits right into to our topics today about data fusion and combining data sources and information from outside sources and fitting models to it. So really appreciate you spending time, the little bit of time you had with us today. It sounds like a really cool initiative and really cool project. So thank you, Lightning Talk presenters. Yeah, as you can see, lots of interesting work happening out there in our field, and let's just continue to roll through it now with some of the longer agenda items we've got free today. Again, I mentioned kind of an ODOT theme today. They're continuing to do a lot of good work in the data analysis and modeling and forecasting areas. So let's start with Shen Shi from ODOT, and he's done some interesting work in speed curve and speed flow analysis. Shen, let's see. Hopefully you've got your slides loaded up. Yeah, I see him there. I'll give you the platform.
Yeah, thank you. Can you hear me clear?
Yes. Yes.
Okay, yeah. Thank you. Thanks for this opportunity. I will continue to talk about the speed flow. Last time we mentioned the line-wise analysis and different understanding of the capacity. We use the CRMS data, central ramp metering system. This data is available in PSU portal and RITIS, and it's a high resolution 20-second data include detailed speed, flow, and occupancy, road occupancy. So that's the last time review. Today, I will talk about the question is how can we capture the free flow speed, breakpoint, and optimized point. So you can see the pattern from the left. At the beginning, the speed is high, is fast, and the horizontal speed. And after the breakpoint, as the volume increasing, the speed will decreasing. And after the optimized point, even the speed is slow, the volume will not increase. Here today, we used some different method. We used constrained estimate, clustering, piecewise regression, and region switching model. And at the beginning, we have to make choice because in literature, we have two options. One is a single region or multiple region to thinking about the relationship between flow and speed. And as far as our purpose is better understand or explain the relationship, we can just choose multiple region, not use a complicated function to fit all the process. You also can see the red point is the variance of residue is increasing along with occupancy. That's is a challenge hard to overcome use single region model. And we start from the easiest concept, free flow speed. It's simple. Seems like very straightforward, just the average speed when the flow is low and moderate. HCM, heavy capacity manual, and the TTI different method. Both of them use some constraint to limit it. We just select the subset of the observation and use the definition of HCM. It's all the data when the volume smaller than breakpoint. But the problem is when we don't know the breakpoint, how can we verify the data set? So HCM gave a default value, suggest use the volume under 500 passenger car per hour per lane. So you can see the picture. This is the density distribution of the volume before of the speed below 500. You can see HCM also mentioned the 1000 is another threshold. So we tried two different threshold. when the volume under 1000 or the volume under 500, you can see for the full lane, the lane one, the volume under when the volume under 1000, the speed average speed very low, and it imply maybe sometimes even the flow is under 1000 is congested or very slow. So it seems like the 500 is better. But another issue is, should we consider cut off the traffic below posted speed limit under 55 and above 75? Because you can see if we choose the add this constraint, the two different free flow speed between 500 miners and 1000 miners very close. Because it makes sense, many low speed is have some special event, extreme weather or accident. Is should we count in the free flow speed measure? And on the right side, 75 is a designed speed, and but in real life, many driving behavior is overspeed, and it's a question I'm keep thinking: should we count this in? So that's for speed, free flow speed. As far as the breakpoint, HCM don't give some method to measure the breakpoint use empirical data. It just suggests equation, but look at the equation, the breakpoint will always larger than 1000. So that imply in last slide, 1000 should not touch the breakpoint. So if we put them on the real data, you can see the lane 1, 2, 3, 4. The two color represent weekend and weekend data. The horizontal or orange line, dash line is the free flow speed we calculate use observation. But look at the intersection with the vertical dash line. The breakpoint use the HCM may be off the real breakpoint. Use our human intelligence, we will maybe choose something like there. Oh, I use maybe here or here is a suitable breakpoint. So how can we use the empirical data to get the breakpoint? We can start from the 1 day, 1 station data. You can look at the 1, 2, 3, 4 full lane and the occupancy, speed, and volume. It's a typical curve. Some reference lines represent the 500 vehicle or speed limit. You can find the peak hour, daytime, nighttime, and the takeaway is sometimes the volume is not is associated with the speed, but not always. Sometimes it's when congested, the volume get down, but sometimes not. But as far as occupancy, it almost simultaneously changed along with the speed. And this is 1 day. When come to multiple day, it's the whole month in June this year, we can see the similar pattern. Even the weekday and weekend have some different, but they just following the different paths go to the congestion, not different relationship between volume and speed and occupancy. So next, previous study give us some inspiration. We know that the speed the diagram between speed and volume is not desirable in functional analysis, because when the when we add here, the speed is insensitive with the change of volume. But when come to congestion, the change of speed don't have too much impact on the volume. So previous study introduced occupancy or density as the mediator. We use volume versus occupancy to find the maximum of the volume that represents the optimized point. And if the relationship between speed and occupancy, we try to capture the turning point, that's the break point. So we can use piecewise regression to capture this point. At the beginning, we let the slope is 0 horizontal, and then we allow they have 3-point turning point to fit the point pattern. So we get some estimate value of volume, speed, and occupancy at the break point or optimized point or even jammed point. But the problem is for some lane after the peak, it's almost flat. For this situation, the knot is very easy. It's not stable. It's very easy to slip to other side like this. And another issue is for the lane 1, it's not. It seems like a special pattern, linear or any curved. It's hard to fit this one. So how to improve this estimation? We often stuck in some one-way window. Introduce occupancy, give us a second wheel. We may want more, and fortunately, this is not a high dimension problem. Only three variable. So we can make a 3D wheel to look at them. It makes sense when the speed is high, is faster, and as far as the volume are growing, and suddenly this jump to the congestion status. So it seems like a clustering analysis is a good tool for this question. We try different ways, and I found that the dbScan is the best one. It's a density-based clustering of application with noise. One reason is sometimes one reason is the time consuming some method. Another is for k-mean or spectral clustering, they should define a k, the number of cluster at first, and after that, try to select best k. But it works for a specific station or specific day. But if we want to cover all the stations, say in I2 or 5, this will not work well. But dbScan, we just need to find a suitable, minimize the number of point and the distance. They can give a uniform evaluation. So you can see if come to multiple days, k-mean will give a very complicated pattern, but dbScan can hold this unsaturated flow as one group and other random walk trajectory to other group. So here is the multiple day for one station use dbScan. Here I use the 15 rolling average of 20 seconds, and for the speed we use the weighted harmonic mean, but it's day by day. If we confound the day variable, it's hard to identify the different levels. And another thing is we don't use the standard regularization. We put the center around the moderate flow, speed, and occupancy. The purpose is to give the faraway point more penalty because we don't want to put the center on the green, the unstable stage. And after many attempts, I found the epsilon 0.2 and the numbers 55 is the best solution. So the beauty of this method is when we come to different station, some station maybe don't meet the very serious congestion. So it's almost blank in this area. And others, the congested area located on different location, but DB scan can quite well capture this different situation. So when we put the different cluster side by side, we can see the cluster level 0 is green is quite a random walking process, and we pretty good capture the stable flow. And for the rest, we can see it seems like two states are switching. So we just combine them together and looking them more later. And after that, if we just focus on the stable flow, the level 1, we redo the piecewise regression, we get improved result. For this case, even this pattern, we can get a quite good estimate of the free flow speed, optimize point, big break point. You can see the major changes happened on the lane 1. And for the maximum volume, it also give a better estimate. So that improves this work much better. And when come to the I-205 northbound healthy stations, we can see they give a similar pattern. The green point means the stable traffic is concentrated on the high speed and low occupancy area. But for the unstable flow or the switching flow, they mixed together and need more investigation. When we explain the data to the I-205 from male point to 2, from 2 to 26, and we can see the distribution, how the dynamic along the male point. Overall, the stable flow, the occupancy always, most of them below 0.1. And another thing, the speed usually is about 50 or 55 positive speed. But when come to volume, this seems like it's hard to separate them. And another way we can calculate how many percentage of in the past months, how many percentage of the unstable or switching flow you can see going along the male point when come to the north, more unstable, congested. But as far as here, we still can not figure out inside the switching flow what is the optimized point, what is the congested point. So we come to the most challenge questions: occupancy, capacity, or called optimized point. In HCM, if we don't have data, just use this formula, it will be a number about 2200. But if we have data, HCM suggests use chapter 26. Firstly, we need to identify the breakdown event and denote the breakdown as 1 and the uncongested as 0, and use Weibull distribution, choose lambda equal 15% to capture to identify the capacity. It is a typical method of survival analysis. When I tried this method, I found this description is far from enough to define a clear breakdown event, because what is sudden, how standard, it's hard to reproduce this method. I tried, I get outcome but I'm not confident because I'm keep thinking the survival analysis is widely used in decay, diabetes, cancer, crash, even crash. Their decay function, it will be a monotone decreasing function. But for our traffic data, it's not like this. So that let me thinking about Puccini's opera. This is story of life or death. In this, there's a conversation between Turandot and Calaf. Turandot said, Enigma have 3, but death is 1. You should give up, otherwise you will be killed. Calaf said, no, Enigma have 3, but life is 1. He believed he will win, and the princess will marry with him. So I guess if the Enigma is 30, he will not take this risk. So that give us some implication. Survival analysis, the event only happened once. Once the event happened, the player will be out. But for traffic analysis, it's periodic time series data. Even decomposite the weekly or daily trend still have we can see the 2 status, congested or uncongested. So it happened again and again, switching back and forth. So it's not like a typical survival analysis situation. So that led we thinking about another way is the region switching model. And recall the Markov chain, the 3 assumption, 3 requirement, memoryless, periodic, ergodic. Our data is quite fit for this situation. And use this model, we don't need to smooth the data. We can choose all days data, and you just use the 20-second. But we need to do is fill the missing gap. Use the last observation carry forward, and it's also is a univariate analysis. And this is the result on speed and occupancy. It can divide the speed to two regime, and further divide the fast speed to 2 level. And compare with previous result, we found the free flow speed and breakpoint speed and occupancy is quite close. The significant change is congested speed and occupancy is much lower than previous estimate. That means use the region switching model, they treated some suddenly jump from uncongestion to congestion, treat as a transition process. This jump will not treat as the regular residue in other method. So that's a major difference. And use this method, we overlap with the previous clustering result. We can recall last time, we can identify the stable flow, the unstable flow, but for the switching group, it's hard to distinguish them. But when we overlap the large volume and faster speed group, we can easy to separate them. And when come to all the stations on 205 northbound, we just use the 3-dimension large or small volume, fast or slow speed, saturated or unsaturated occupancy. We can get the 8 different plot. It seems like the small volume, fast speed, unsaturated can represent the free flow speed. And as far as the large volume, fast speed, this is saturated, unsaturated. You can see the green point catch the last moment of high volume before congested. That's I think that's a major contribution of this method. Otherwise, we could miss the last moment. So when come to the Moyle point, we can see if we just select the first large saturated group, we can see majorly from Moyle point 2 to 26, the occupancy is between 0.2 and 0.1. And another thing I find interesting is the different color is the lane left, right, or middle. We find that the right lane, when reach the moment before congestion, the right lane has the fastest. That makes sense. When at that moment, the right lane, the driver can choose to exit to the freeway, but the left lane driver will start there. So that I guess that makes sense. And people maybe can interpret this result better than me. So at the end, I want to say we collect the data from some objective measure, flow rate, speed, and occupancy. But when come to free flow speed, breakpoint, optimized point, or congestion, there are some indicators. We hope them represent some meaning, but for them, some kind of is subjective. Similar with the different method. Each method have their advantages, clustering, regression, or Bayesian method. But when we apply this method, we will find there's too much things we need to make a choice, not like the simple as the we just follow each step by step. The last thing I want to say is you may think the previous analysis too complicated. In real life, how can we use a better way to get this indicator? I will suggest if you want to get empirical free flow speed, choose the speed between positive speed and 75, and add the constraint occupancy smaller than 0.1. As far as for the I-205 northbound, it works well, and you can recalculate the same value when the occupancy is smaller than 0.05. If the two result is very close, it means this location is very typical. You can use this free flow speed. But as far as the breakpoint, it seems like no simple way to capture it. For the occupancy or capacity, I guess easy way is we just choose the speed, all the observation between 55 and 60 speed, and that means very close to the congestion area. And we can add a more constraint of occupancy between 0.1 and 2. But I will suggest we don't use a point estimate. We will get an interval to represent the uncertainty of the moment before congestion. For the congestion part, maybe the most easy way is just count all the observation below 55 and cut off the occupancy smaller than 0.1. That strictly is not congestion. It includes two states at least. Is unstable random walking and congested status. So, but it's efficient, easy way to get estimate. And that's what I want to talk today. Thank you for your time. And please let me know if you find me misunderstand anything. Thank you.
Okay, thank you, Shen. great work. Lots of data mining here, and really appreciate you walking through all the modeling and analysis steps and different kind of regression models that you looked at. I believe we have a question in the chat. I have a question or two as well, but let's start with the chat. Dan Cody mentions he likes your work. Do you have any information that he can share with WashDOT colleagues? So, yeah, maybe you can just address that at face value. Shen.
Yeah, I think I just tried different method to following the HCM, try to use the empirical data to try different methods. So what I say today, I think it should not be any concurrent. Is still need to explore. So if you want to share the method, no problem. But don't choose my result as any concurrent from ODOT. That's just my personal exploration. Yeah.
Okay. Well, thank you, Shen, for addressing that. And maybe well, looks like we have another question here from Li-Ning before I get into mine. He's not familiar with the term occupancy used in speed curve analysis. If you could clarify that, and how is it different than capacity?
Occupancy means it's a original measure in the data. Is the measure the how many times the detector is occupied by vehicle. It's I forgot the name. It's similar with the density, road density. We use the how many vehicle is occupied on the road density. Each per mile, how many vehicle on the road is density. How many time is occupied by the vehicle is occupancy. So, but the difference is density is calculated from the volume over speed, but occupancy is directly observed on the road. So that's it would be a better measure. It's different with the capacity. Capacity means some moment the road reach their limitations. They cannot contain more vehicle on a decent speed. That's different.
Is it fair to say that like jam density is similar to capacity, or are those not interchangeable?
It's changeable. Last time I mentioned they're roughly a linear relationship. It's the coefficient is about 0.6. Some research use the relationship between density and occupancy to measure how many trucks on the road. Actually, the 0.6 is roughly the because maybe one truck represents two vehicle passenger car, but they occupy the road time is similar. So it's a very interesting topic, but I didn't cover today. Surrogate, I guess the word is surrogate. Occupancy and density is a surrogate.
Okay. So, yeah, Li-Ming kind of mentions here, and I was interested in it as well, and maybe others too. What are your next steps for the work? Do you plan to publish it? And maybe you could talk about what how you see ODOT using this as an agency, using this work.
I'm still looking forward to more feedback from expert. I want to expand this analysis to at least the region 1 or freeway. Now it's only on the I-205 northbound. I hope I can get general method to help everyone to better understand the empirical traffic flow. Yeah.
So as I understand it, your samples were taken on 205 only. Is that right?
Actually, the ITS CRMS data in region 1, there's a lot of stations.
Okay.
Because the data is very large, I just play with the data on 205 northbound, the 1 month data, because 20-second data is very large.
Yeah.
Mm.
It seems like, I appreciate the segmentation you did by the different lane configurations and how maybe an inside lane or middle lane or outside lane, how they had different, I guess, breaking points is what you referred to them as. I'm wondering, like, how to explain that? Like, what do you think might be some reasons as to why some of those different breaking points occur? I guess one thought that came to my mind was maybe a relationship between upstream and downstream interchanges and just the merging and diverging effects that kind of influence those different lanes and their different breaking points. Is that something that you can tease out of the data, or maybe you have already?
I can share that page. Actually, I find HCM suggests some ramp lane should use different method, because in this area, this lane 1 is very close to the ramp. So after some in-field observation, I found because it's close to the entrance and exit, so the speed is constrained by their situation. So
Yeah.
What I found is in this case, not all the I-205 have 4 lanes. This location have 4, and that means the middle lane is more robust. Driver can choose merge or leave and change the lane, but for the far left lane, it's very sensitive. Once even they have a highest speed, it's very easy to interrupt by some interruption or traffic. So you can see the free flow come to the break point. The lane 2 and 3 have a very long segment when come to break point. That means they are more robust. But for lane 1 and 4, they are more easy to end this period, enter sacrifice the speed and exchange some flow. That's so each lane have different characteristic. I'm trying to figure out is there any general pattern in region 1 freeway? Yeah.
I could see the use for kind of rolling this up, and it's interesting to look at lane by lane, but also being able to kind of roll it up into a freeway segment, right? Where irregardless of number of lanes, this is generally how this performs. And to that point, have you guys talked about, like, I'd be interested in I don't know, maybe looking at these charts with an overlay of maybe the BPR function that we use for our volume delay curves on freeways, and just to see how well, I guess in particular, that function in our assignment models does kind of relative to the findings you have here. I'm not sure if you've gotten there yet, but that would be interesting to to see, especially at those at that breaking point, right?
Yeah.
So Kyle and Shen, I hate to cut us off, but we're at time for this item. We need to get moved on.
Thank you.
Thank you very much.
Thank you, Shen. Okay, moving right along here. Let's get into let's get off the freeways and onto pedestrian movements. So looking at pedestrian data for modeling, Josh Roll and Alex Bettinardi. Take it away, guys.
Yeah, great. Yeah, thanks, Kyle. Thanks, everyone. So I'm going to kick us off introducing the second, well, I don't know what agenda item are we on? About 4 or 5 or whatever, 4th or 5th agenda item related to PED data, like you were saying. So Josh brought, for anyone with a great OMUG memory, about a year ago, Josh brought a handful of new data elements to OMUG to share, and this was one of them. And so we're continuing that conversation around, you know, how that data is progressing and you know, how we see it being used in models next. So Josh, if you want to move to the next slide. So agenda-wise, just talk a little bit about kind of the motivations behind you know, starting to use this data more. What's going into the data, how we're going to use an activity-based models, then we'll open it up to questions. So go ahead, next slide. So so as we've been developing our as we've been moving towards the next set of travel demand models, our activity-based models, we've been having a metrics conversation around you know, how can we improve the information that comes out of our tools. That metrics conversation has been framed up around the goal areas in the Oregon Transportation Plan, but those goal areas are very common across all of the regional transportation plans in the state. So very common themes: safety, equity, climate, mobility, community, economic, you know, improving economic conditions and preserving the system. So these are the goal areas in the Oregon Transportation Plan, and areas that we've been working to see what we can do to better improve the information that comes out of our models in each of these categories. So today we're focusing on the safety piece, and what our metrics conversation has kind of highlighted is that if we want to do a better job around safety, then we have to do a better job on understanding person miles traveled across all modes, and then, you know, for cars it's kind of a given what route they are on, but for biking and walking and our active modes, really understanding how many miles people are out there by the route that they're taking, so we can understand the exposure information, where these where individuals are, and what they're up against from the heavy vehicles that cause the safety issues. So yeah, thanks, Josh. So you know, to summarize that point, our current models don't represent. I think Josh is trying to get the little graphic. I don't know why that graphic won't. He's got a really cool little climbing. Yeah, the little chart's supposed to climb. Sorry, Josh. It is cool when it happens. Let's see. So to summarize, our current models don't represent pedestrian traffic very well, and so, you know, the kind of a key objective here is to and it's hard to have our models estimate pedestrian travel if we don't have the data. So we have you know, we have data now that is we can start to use, and so hopefully we can start to get better in representing our pedestrian travel, which we need to better capture safety metrics. And in addition to getting better safety information out, there's also across the Oregon Transportation Plan, there's 3 specific focus areas: safety, equity, and climate. And so, you know, more broadly, this data can be used to, from the safety perspective, like we kind of already captured, if we have this information, that we can better understand the risk exposure. So it's kind of clearly there as a safety piece, but also from an equity piece. Lower income populations walk more. So if we better understand pedestrian movement, we'll better capture the travel movement and behavior of lower income population. And then on a climate side, if we better understand active transportation modes and what influences them, we can better understand the outcomes on VMT and GHG production when different policies and projects around improving active modes are on the table. So these are all kind of the motivations behind why this data might be, or why we should be assembling it and then using it. So with that, Josh, I'll transition to you. If there's anything else you want to say on the motivations, go for it. But then we have the data piece here.
Yeah, no, that's great, Alex. Thanks. Hey, everybody. I know a lot of folks on the call, but my name is Josh Roll, and I'm a research coordinator with ODOT's research unit. And we've been working over the years on trying to better represent traffic flows for people walking and biking through our models, through our travel and traffic monitoring programs. We've helped a couple MPOs set up bike and pedestrian count programs. The first one in Eugene, Springfield area was to help validate the new bicycle route choice model that we adapted from research from Portland State and that the folks at Portland Metro had implemented. And so we've been working on this for years. Thankfully, the sort of state of the practice and things like the Federal Highways Traffic Monitoring Guide have advanced. The latest traffic monitoring guide has all the protocols and things that potential traffic count programs that would count bikes and peds would need to implement those programs. The challenge has just been resources. We're all under this incredibly fiscally constrained environment that makes doing something that the feds don't require, the state doesn't require, almost impossible. But that context aside, we've still continued to try and find ways to better monitor the system for those non-motorized modes, those active modes, using available infrastructure if possible. So one of the projects that I've come to this group and others to talk about over the last probably year or so is a project where we had a research team from Portland State and Utah State University developed some methods to take our push button data at traffic signals and turn those into estimates of pedestrian volume. This was building on work that Utah DOT had done pre-pandemic. And so we had kicked off this project just during the pandemic, I think late 2020, early 2021. And that's relevant for some transferability of some of the methods from Utah, which I'll talk about I guess here on this slide. But the report has been finished. That work has been done. There's a full technical report on our website. I'll also have a link at the end to a video of Sarisha Katuri, who led that work from PSU's side, presenting at a PSU Friday seminar. But the essence, right, is that people go to a signal to cross, oftentimes pushing a push button. And when you correlate those or relate those to actual counts of the people using the system, there's a pretty strong relationship. It's not one-to-one. You got to do some things to the push buttons to filter out all of the anxious elbow pushes as people sit there waiting, thinking that the more times you push it, the faster the light will turn for you. So there's some filtering work that was tested, some filtering methods that were tested, and then a bunch of different model specs that were tested, which I'll talk about. But again, the essence is taking those push buttons, which we have at least on ODOT signal system at almost 700 locations, growing every day. We'll have up to like 1,000 of we have about 1,000 signals we manage. There's some problems going on with a transition to the backend database that stores these data, but at some point we'll have 1,000 locations collecting these data, mostly good data. I mean, you still have to, there's still buttons that stick and hardware issues and stuff that you got to filter out like any traffic count device, but good data in a lot of places, coupled with the data from local jurisdictions. For instance, PBOT is also working on getting all these data integrated. We'll have like 2,000 traffic signals feeding these data. And if we think of them as permanent pedestrian counters, having 2,000 on-street pedestrian counters so far surpasses my wildest dreams of the number of devices we would have monitoring PEDs of what I would have thought about 5 years ago. So it's a pretty incredible set of data. Still some work to get it all integrated, but the work we had the team at Utah State and Portland State do was go out. We collected about 900 hours of observed data, interface that with the push buttons at those locations, tested a couple different ways of counting the push buttons. There's different phases that you can count in the signal controller. That's this like A45, A45A. These are also different ways of filtering the data. Do you start filtering after, or do you stop counting for 10 seconds or 5 seconds or 15 milliseconds? So we tested all those. That's what these A, B, C different configurations are. Different model specs, so linear, piecewise, quadratic. And then we have performance measures here, just raw correlation of the counts and the signals, counts being the observed empirical data, RMSE, mean average error, and a couple different ways of looking at that. And then also doing this like using like a holdout approach where you take part of your data, estimate a model, and then try to predict your fold that you left out. And what we landed on was the quadratic, which was the same as what they found in Utah. And I'll just mention a bit about the Utah research. Utah has traffic cameras at most of their intersections. And so we're accessible for the work that was done there. And they, from those video, gleaned the number of actual pedestrians, the empirical counts, and they used something like 10,000 hours of data to sort of build their model. And let's see. And one of the things that the research that Oregon did, that I coordinated here, was like test their models using our data and vice versa, and the results were remarkably similar, which showed that both there's spatial transferability of these methods, but also temporal transferability, especially given that work in Utah was pre-pandemic. And ours was post-pandemic, and whether or not people are a little more hesitant to touch buttons and that sort of thing. So a lot of promising results from the work that was done, and now we're moving into implementation. And so I'll share the link to this very simple dashboard that I crafted here at the end. But we have these data up, factored. We have them for multiple years. You can cruise around on this dashboard. We have another one that Sean Strasser, one of our signal, like very data savvy signals guy, had put together. I can't find the one that's like public facing. I got the one that's for internal use, but ultimately, oh, we have a question. Somebody stepped on a cat. Okay. Ultimately, these data are going to go into the BikePed data portal at Portland State. So we've been working with the portal group there. We have some funding together, so everything will be wrapped into that platform, hopefully in the next 6 months. We're working with them, trying to get the data pipeline set up. And then there's still some anomaly detection work that we need to do that I mentioned, when buttons stick or other strange things that happen. But we're already looking to use these data in the purpose that Alex mentioned, that he'll get into a little bit more next. But also in some of the work we're doing on building predictive crash models for PEDs. We have all the data constructed for that, which I'll talk about in the next presentation. But for now, I'll turn it back to Alex. He can talk about the model calibration that we're planning.
Yeah. So on the model side, I think for a long time, I think our travel models have had an autofocus, but also there's we've had the easy out in that there's not a whole lot of data available. So, even if we wanted to do a great job with PEDs and bikes, we don't really know how they're moving around. Well, sorry, say PEDs this fine, active transportation, but PEDs in this particular case, if we want to do a good job understanding where PEDs, how PEDs move around the system, well, we didn't really have the data to QC it or develop it. So we didn't have an egg to raise a chicken, but now we have the egg, so we can have chickens. So if you go to the next slide, Josh. So now that we have chickens, so now the next step is we have at least 5 steps. I'm sure we could daydream more here, but the first thing we need to do, we have I think most of our MPO travel models have pedestrian ODs. We just don't assign them. At least I'm not aware of us assigning them to the network, putting them on routes. So step 1, let's assign them to the routes and see what happens, probably using a shortest path or something similar. We now have the observed data that we've never had before, so we can start to QC those assignments against observed data and see, I imagine we're going to be pretty off in some places because a shortest path won't consider how terrifying it is to cross a certain intersection, and that most people would deviate out of the way of that intersection. Our models also, I'll get to this in a second, but our models also don't have what I believe is probably a really large percentage of pedestrian trips, which are loop trips, trips that you make, just to get exercise or walk the dog. Those aren't in, so we probably also are going to have an issue with those, kind of recreational or optional trips or loop trips or whatever you want to call them. So we're going to have some, some issues, and that, I think that step 3 will be what we start to determine, what's different and why do we think it's different. Luckily for us, in 2025, we're entering an estimation phase, so this times out well. If we see some differences and we think we can correct for them, we can start to bring in additional network attribution, like some kind of quality metrics. We've talked about research elements to better represent loop trips. We can start to bring some of these pieces in to try and close some of these gaps that we identify in step 3, and then if we determine that that if we're able to better pull in the information that helps explain where people are traveling, then we can finalize these new models with the network inventory and attribution that gives the models the explanatory power we need to understand where PEDs how PEDs are using the system. So so then in the end, we'll have improved model representation of pedestrians using the systems, and therefore we'll have the safety metrics and estimates that we need to be faithful to the desire to improve our safety metrics. So then, Josh, if you move to the next slide, this is just conceptual. I had hoped that maybe we could have had something a little bit more concrete to share here about what the step 1 and step 2 look like. Of step 1, assigning our current pedestrian flows, and then assessing where we're at. I believe shortly after some kind of OMC meeting, we could bring that comparison back for some of our models. But basically, this is what it looks like. The pedestrian information that we have right now, for various reasons, we could definitely answer in a Q&A if we want to. It's an intersection number, not a crossing number, and so we would have to total up our model, the amount of pedestrian movement moving through a node, and we would total up pedestrian movements at a node. We would then compare it to the amount of pedestrian movements moving through an intersection/node that we're getting from the actuation data, and we could start to do some scatter plots and spatial mapping to see where we're low, where we're high, things like that. So that's what step 1 and step 2 would look like. This is just kind of comparing that we have 2 spots in a map and that you can pull this information, but we need to do it kind of globally and understand it so that we can bring step 1 and 2 back to this group later. So and then when we move into step 3 and step 4, we have this great new survey that's going to have a ton of great information. So unlike surveys in the past, we'll have more detailed route choice representation specifically for active modes, which we've never had before. We're going to have this current survey went much farther in properly capturing all Oregonians of all types from an equity focused standpoint. So we'll have a much better canvassing of the types of Oregonians using the system, and we'll also have a better a lot of This survey is cell phone based. The paper surveys of the past had the potential or the issue of trips being skipped if they didn't seem important or too small. And so now we have apps that we're tracking where individuals moved. And so we're going to have a more complete representation of all of these little trips that were happening, all of the uses of the system, the different modes that were being used. So we're going to have a ton of great information with the survey that can help improve our abilities to represent all travelers. Work is still required. The survey doesn't quite answer everything, so we have to supplement and augment that survey. We need the networks behind the survey, and we need the inventory data on those networks that represent quality for the quality of the path for biking and walking. So that's going to require some inventory work. Luckily, the state is pushing forward a pretty hefty contract right now to do a lot of inventory work. Hopefully the bulk of that lift in our MPO regions across the state. So hopefully we have somewhat of an easy-ish answer there. Let's see, like I mentioned earlier, there's also, when it comes to pedestrian movement, some additional research needed around, loop trips that are missing in our models, weekend movement, visitor movement. I'm not saying that we have to do all this, but this is just places where we would, if we really wanted to understand pedestrian movement, we might need to close some further gaps there that the survey, the survey would cover weekends. Our models don't cover weekends, doesn't cover visitors. So there's just some pieces there. And then, what was my last point? Motivations, no choice, but understood. I think it's just, kind of getting at that missing inventory data around, is it like, what kind of trip is it? Is it is it a choice trip or I guess I was thinking about captive trips. Like, am I walking because I want to get the exercise and I have a car at home? Or am I walking because my auto ownership is 0 and this is my best way to get there? So understanding kind of how people make choices under different conditions and different availability of options. And then also, I was listing here the last bullet. There might be gender preferences from personal safety issues. Men be more likely to bike. I think see the survey says I think men are more likely to walk in different situations than women would be. So, anyways, things that we would need to tease out there. So as I list all of that, I meant to mention as I looked at all of that, you could very well be thinking, well, Alex, I don't agree with that bullet, or where is this bullet? And so that's the next slide. Yeah, go ahead, Josh. So we're done talking. We're curious from this group of that bullet list that I just sent. Are there other research things that you pop to mind? We're getting close to the research cycle. There's a lot that needs to be done here. So we're very curious what other ideas there are around how to fill these gaps. And what the gaps you anticipate are. We're also, as Josh and I were working this, it kind of became evident that this signal data that's being used is across all days. I think you're saying 20 minutes, Josh. Is that what you're saying? 20-minute bins. So highly temporally detailed, and for modeling work, that's super overkill. So, curious, how would you, how are you interested in using this data? What data format would you like it in? What time periods would be helpful? I've started talking with Josh, thinking about kind of a Wednesday in May, hour bins probably, those kinds of things. Ultimately, maybe we're looking at weekends for some future research. It's all there, but kind of initially, what formats, what aggregations would you be interested in? There's a final slide about some of the resources that Josh mentioned, but before we move there, I think we're opening it up to questions, and I'm done talking.
Yeah, and just
thanks, guys.
Sorry, Kyle, and just to emphasize, one of the asks here is just about, or two of them rather, is just about what are those questions that need somewhat of a full research effort to uncover. We have the research program here at ODOT preparing in the fall to start writing research proposals that would come to our office and be considered for funding. And then the second piece is, what are the metrics specifically within the push button derived PED volume estimates that are necessary for you and any of the work you're doing in planning or modeling, so that we can build that type of functionality into the user interface of the Bike Ped data portal or the Our Shiny app or whatever, that will be a short-term solution, that Our Shiny app, but the Bike Ped portal being a longer-term one, and folks that can do something probably more sophisticated than what I can do in Our Shiny. So those are two specific asks along with those bullets. So
in terms of these questions, Josh and Alex, if people do have ideas, they would just get a hold of you guys via email, or what's the best way to, I guess, address these questions if people want to follow up with you on this?
Well, I personally assumed everyone would be exactly ready right now to answer these questions, and we would just deal with it now. But I think email would be great if people want to react to this.
Okay, maybe you guys could put your email addresses in the chat box. Quick question for Carol, just doing a time check here. How much time do we have for Q&A on this particular topic?
Yeah, we're good. We have another 10 minutes if there's questions. Yeah.
Great. Do you want to, Carol, do you want to scroll through the chat box and see? It looks like maybe Ray had a question that's going to be maybe pertinent to our data fusion topic that comes up next.
Yeah, Ray has a couple questions in there.
I'm happy to take them. Yeah, Ray, we're going to talk about next how to fuse multiple data sources and train models on these push buttons, in addition to some other data, which we haven't fully compiled yet, in order to estimate pedestrian volumes at locations where we don't have counts. So we'll talk a little bit about that, in addition to an evaluation of a third-party data product from Replica that also has estimates of PED volumes. So so the short answer is we're going to use these data to estimate in those locations where we don't have data. We'll also be bringing in some short duration counts. So that's an ask I have of folks of like, hey, what do you got for short duration counts? Ideally 16 hours or more. But and then in terms of signal controllers, the latest ATCs are the ones that ODOT's been installing and that have the capability of storing these data and housing them somewhere. So that's the big rub. I know that ODOT struggled, at least initially, in storing the data, that the state data center at first was like, sure, give us all the phases. But it turns out it's a ton of data, and they began squawking soon after we were doing the transition, maybe a year and a half ago. And so we have since had to come up with a different plan, including aggregating some of the data. And so instead of collecting every phase, things are collected in 15-minute bins, which created some problems because we needed the filtering method to be applied to the raw data before it got aggregated. And so some things to work through there. But hopefully that answers your questions. I'm curious on what Salem and Salem-Kaiser area signals look like, because the more signals signal folks we can get thinking about this as they're selecting technology and back-end databases, the better the capability will be over time for using those data for this purpose.
Yeah, just on that, I know Salem's moved to 2070s and some of the newer adaptives. And we have had conversations with Salem, and maybe you, I don't remember, about capturing that data from the push buttons. Also, right. The RFBs used to collect the data, and then they got bought, and so that data is you either have to pay a subscription to get to it, or it's no longer available from the vendor, which would be another good one. Mid-block
totally
would be very useful.
Yeah, that's right. I remember that conversation now, and if I remember, the data's available, but there's no centralized database that the data are flowing to. So you would need somebody to go out to each controller and collect the data. And,
right.
That's been something that's prevented us from considering this approach before, because of that need. And so that's been another motivation for moving towards this approach for monitoring PEDs, is because all these data are being stored centrally, making the data accessible.
And it might also be the controller software, not necessarily the controller, because I know ODOT and Salem run two different programs, and they might just deal with collecting the data differently. And so each jurisdiction, you'd have to ask, what's your controller and what sort of software are you using, and does it collect it and store it, et cetera?
Right.
Okay, let's see. Any other questions from the group to either Alex or Josh?
Kyle, I got a question.
Sure.
I don't know.
Jeff,
Actually, I'm not sure it's a question, but it's research I would like to see pursued or not pursued. The first thing I want to say is I hope the fact that these push buttons are a valuable data source doesn't induce ODOT to install more push buttons, and that the push buttons will only be installed in locations where they're necessary. And that kind of leads into my interest in or research I would like to see pursued, is looking at the variation between the ratio of crossings to push button pushes, and looking at what are the characteristics of locations where that ratio is high or low, and specifically thinking about the locations where the ratio is high, that a lot of people are crossing without using the button. It's probably a location where the push button is not necessary or counterproductive, or some other intervention would need to be pursued to figure out why people aren't using the push button. Any thoughts about that?
Well, I would just say I don't think ODOT's modeling work has anything to do with how ODOT makes decisions on push button placements. I would just, perhaps if that adds any comfort. Go ahead, Josh.
Yeah. Well, lots of interesting questions, Jeff. I think what we need to do for this method to keep working is to continue to, like, every couple years do additional data collection and comparison and see how the factors are working. I think there are going to be conditions where we don't pick it up well, like the total volume, because of big groups or conditions that just aren't the average. And it kind of gets into a question about how good is good enough, that we talk a lot about with some of these methods for estimating bike and walk volumes, where because the numbers are so low in a lot of cases. I mean, you'll see in our Shiny app that I'll put out here, like, there are places where, based on these methods, we're looking at just a few a day on sort of the annual average, a few PEDs a day. And a lot of those are just like around really inhospitable places where you wouldn't expect a lot of activity. And so if you're now, using those data, and if you're off by 100% or even 1,000%, like, does it matter that it's 20 and not 2? So there's questions like that get into, I think, testing the data in different applications. I mentioned we're going through with putting these into safety performance functions to see how they work, and whether or not the uncertainty in the estimate, how much uncertainty matters. In terms of not installing these, I hear them called beg buttons. I think, Ray, you just said that too. And I am in my mindset, I always follow this sort of like PBOT, Portland Bureau of Transportation's hierarchy of users, where it's certainly PEDs first, bike second, transit, and so on. And I think in order for us to meet any of our safety, climate, and equity goals, we have to adhere to that framework. And I know that ODOT, being a manager of highways, we don't always necessarily do that, especially historically. But I'm not sure I agree with the term beg button there are certainly more advanced ways to give pedestrians' preference. But for now, with like arterials, I don't know what else. I mean, again, barring cool advanced, computer vision technology or LiDAR or something, I feel like these are good systems, and especially if they have responsiveness where after you push it, you don't wait another 3 minutes and you're waiting, 15 seconds or less. That's great, right? But whether or not any of the demand on the data would inform where we put signals and push buttons, we're probably not that well organized. So I don't think that's going to happen. Hopefully that answers some of your questions, Jeff. But happy to talk more, especially about any of the research ideas that might be bouncing around your brain.
Are all these locations at intersections where the vehicles are also, stopping on a regular basis, or any of them mid-block, like pedestrian?
Yeah, they're all intersections, no RFBs, unfortunately. And there's, we'll talk about this in the next presentation here, just about how well we can estimate at non-signalized locations, which may have a, induced demand sort of effect for PEDs, estimating at non-signalized locations and how well that's going to work, and how we'll test and validate how well that works, because that's certainly a question.
Hey, Josh, for the data, did they consider location of bus stops in relation to the intersection, and then see if there's APC data from the transit vehicle to see if there's a correlation between?
Sure.
Yeah.
Well, when the research team that built the factor methods for the push button data tried doing that in different sort of clusters and buckets. We tried like place types. We did some different buckets by like proximity to transit stops. And the one using place types did actually work a little better in terms of some of the performance measures. But we felt like it was maybe the performance gain wasn't worth the complications of applying them. So we went away from it. But in terms of then general sort of, correlation of or relationship between PED volumes and transit stops, will show in the next presentation how that is definitely a useful measure. We have great data on transit stops. We don't have great data statewide on transit ridership. So we have some data in some places. That's another project that we did many years ago, was building a data standard for transit ridership at the stop level that interfaced with GTFS. We call it GTFS Ride. We would love to see more transit agencies get on that standard, so I'll put a plug-in for that, so that those data can be uniformly collected across the state and used for things like this, among other uses. But definitely a relationship that we know exists and that we're trying to test out with the data fusion work.
Well, I think that's a good segue then into the next topic, Josh, since you mentioned the data fusion piece. It seems like maybe we're hitting a few of your bullet points anyways here as we go on with this Q&A. So let's move from the pedestrian data from modeling onto the data fusion topic. And I think Josh has some interesting information to share about just some comparisons he's done with the signal derived PED volumes against some estimates that are coming out of Replica. And so with that, Josh, take it away.
Yeah. Well, this will be a short presentation. I'm going to go over a little of what we've done so far, and we have 2 full presentations here, so this will be quick and a lot of information, and everyone's stomachs are probably starting to grumble for lunch, so I'll go quick. But we're going to talk about the use of these data, these push button derived PED volume data, in building a bigger data fusion model so we can forecast out estimates of pedestrian volume in places we don't have data. And then also just a little teaser on the work that we've just begun to evaluate a third-party data platform's PED volume estimates. and that's the Replica platform, which I know Portland Metro's had some experience with. So in time, hopefully we can chat more about what we got going on and how we're doing it. But I'll share some here. So similar motivations as were shared for the work that Alex and I presented on the last presentation. So, we did some work a couple of years ago now where trying to understand the relationship between traffic safety and social equity. A number of different analyses were performed in that work, which I can share the link to that full technical report at some point. But one of the analysis that was done was sort of a zonal analysis of where pedestrian injury occurs. We did this at the census tract level, combining measures of the census tract around, traffic density, other built environmental factors, and then sociodemographic variables, income and race being ones that were predictive of where pedestrian injuries occur, even after controlling those traffic exposure and built environmental variables. We got all the way to using those models in a predictive fashion with an example here for the Salem metro areas showing where the highest and least likelihood of pedestrian injuries would occur at the tract level. Well, that's interesting on sort of a very 10,000 foot view, but when you're trying to put placements of interventions, knowing a whole census tract isn't all that useful. So the work that we did a few years ago is transitioned into a second phase where we're building intersection and segment level predictive crash models to help with network screening, before and after studies, and a few other applications. In order to get there, though, we need exposure measures for pedestrians. And so we are taking these push button data and integrating them with some of the other data we've put together for the safety performance work and see how things work. So we're at the really just a couple weeks into that data fusion estimation work. So I'll share a little teaser of that. And then thirdly, and again, this could be a whole presentation on its own, I just want to talk about and let folks know that we are evaluating against those push buttons estimates from Replica. Let's see if I got some more on Replica. I'll talk more about how Replica does their thing for folks who are uninitiated. So this is a little of the workflow for putting the data together for our safety performance function project and data that will also be used in some of the data fusion work. So, we're taking as a base network a version of the OSM that has some volumes on it from INRIX, which is the analytics company, transportation analytics company that does our speed data. We're using that. We're conflating with HPMS data. Those are sort of the data of record for where our volumes are. Putting the speed measures on, again, from INRIX onto those data, and then building out intersection inventory, road segment inventory with other variables about number of lanes, speed limits, medians, other important measures that we'd want to include in our safety analysis. So we're just now getting into the data development stages 5 and 6 here in this chart, where we're adding information about transit, sidewalks, pedestrian crossings, because we don't have that yet. But we've already, with the data we've had available statewide, or at least in the urban areas, the sort of purview of the safety analytic project is the 66 urban areas in the state. Since about 90% of pedestrian injuries occur in urban areas, we kept it to just urban areas as our geography. This just kind of goes into a little more detail of all of what we're combining. I mentioned a bunch of these, of course, the crash data. We're also bringing in smart location data. They have a lot of good information in the EPA's SLD data around accessibility and the sort of the 5 or 6 or whatever 7 Ds, density, diversity, those sorts of things that are useful proxies for pedestrian activity, which is what we've used so far. Ultimately, we'll be conflating and joining information about pedestrian infrastructure data on top of these data, at least where those data are available before we do the big CFEC multimodal inventory process. I have a dashboard I can share. You can peruse some of these data. The intersections for Portland metro area will render. The segments won't. I still need to fix that. So for Portland area folks, you'll have to be happy looking at just intersection data. So data fusion, what's data fusion? I feel like this is like an overly a cool term for just some of what were initially like decades ago, the preliminary kind of travel demand models, where you're just taking a count of traffic like at an intersection on a segment, and then as a function of other in sort of environmental built environment variables, predicting the volume at that site. And so data fusion, just a fancy way of saying we're predicting the traffic count as a function of a bunch of other variables that we have data on across the network. And so a picture here from a project we did out in Bend, deploying these methods. You got your traffic counts up here. We got measures of access to jobs and network centrality, other network level features, information about what type of segment it is, how many lanes, what kind of functional classification. We combine that all. We use statistical model approaches like regression, but we've also had pretty good success with machine learning techniques too. So that's sort of what we're talking about when we're talking about data fusion. One of the issues with pedestrian modeling is that we don't have a lot of data. Alex mentioned this about calibrating our models. So currently we have about 600 or 700 of these sites around the state at signals. We have short duration counts that we haven't totally processed yet. And then we do have permanent count sites, and we've had them for years on off-street paths around the state. And we took some time many years ago to integrate those data into a single database. The problem with those off-street paths is that the traffic patterns in those locations are not always the best to use for traffic factoring, short duration counts on street facilities, because they're just totally different patterns where you have a lot more recreational users on those facilities. And that's another really great thing about these push button data, that they're on street locations. So we're combining those data about the intersections, what the vehicle volume is, what are the INRIX operational speeds, what kind of intersection is it, a 3-leg, 4-leg. We have other measures that come from a zonal, level for sure, from census block groups, from the smart location database that we're putting on top of those points, if they're intersections or segments. For the segment level models, and then trying to estimate and figure out what the relationship is with all of those variables and the pedestrian volume. So here's just a very preliminary set of models where we're looking at the effect of all of these measures on the left and the relationship with pedestrian volume. So the higher, this one has stuck out is somewhat strange. I think we'll probably have some unobserved variable bias here, but the more vehicle volume, the more we'd expect the pedestrian volume to be. I think we're missing something there that we're trying to account for with this interchange proximity variable, which is going in the right direction, but a more reasonable sign with the max speed. The higher the speed, the less the ped volume. And so maybe if there's a lot of cars, but they're all moving very slow, maybe we would expect more pedestrian volume. Again, these are preliminary models, so as we dig into this, we'll see. Intersection characteristics, so 4-leg versus 3-leg, interchanges, a lot less volume expected. And then some of the sociodemographic information here, we have the higher the volume, the higher the income, at least at the block group level, at that intersection, the less pedestrian volume. More employment, this is a spurious one too. It's significant, but it's telling us that total volume, pedestrian volume is going to be less in higher employment areas. We may need to specify this feature differently, maybe look at density, maybe look at different types of employment. Population looks like it's in the right direction, more population, more people walking in that location. There's a measure we have in SLD called the National Walkability Index. This isn't a measure of safety or anything. It's just a measure of kind of diversity of uses. There's some transit mixed in there too. So the higher the walkability, the higher the traffic volume for PEDs. To your question, Ray, about transit stop proximity, we're just looking at the total number of stops within 50 meters here, more pedestrian volumes. We have measures from the census around journey to work. So that the more people taking transit, the more, at least for work, the more people we'd expect walking at that intersection. Journey to work for walk trips, not significant, not in the direction we'd expect. And then a couple other fun data points that we're putting in. So, as a DOT, and this goes for all the local agencies, we have free access to Strava data. Strava data has been useful for predicting where bike activity happens. It's bias data. We know it's older men, for at least the biking, probably higher income, taking mostly recreational trips. So we're using the walk, jog, and run trips and seeing if they're going to be useful. They do add a little bit of explanatory power compared, using the R squared as a metric there. We're using the total Strava trip count here and then the commute count trip here. And so you see there's a little degradation in model performance using that measured variation or explanatory power when we use the commute trips, which is too bad. So we go back to using the Strava trips here in some of these models, adding a couple different measures for like if there's an arterial entering that segment or entering that intersection. And then so our first blush here at looking at the replica data, we use those as just an input feature here in these data fusion models. We lose some observations because they didn't, for some reason, give us their estimates at every signalized intersection we asked for, but it does boost the explanatory power. So that's a little of where we're at with data fusion. The idea then is to take this model, we apply it to every intersection that we have in all the urban areas for volume estimates. But we'll do a lot more work testing using cross-validation, and which is a much better way to understand the accuracy of your model and stuff that we can share in the future. So real quick, don't have to tell probably a lot of the Metro folks about what Replica is, because I know you guys have had experience, but Replica is a big, one of these private data firms that basically buys every piece of information about you and puts it together to build a really cool activity-based model. They have types of data on us that I think most of us would love to have, although I question whether or not our privacy is being violated with some of the data out there. It's open, it's available for purchase. There's no laws against it, so they're not breaking any rules, but it's unclear if that's going to be the regulatory atmosphere going forward. However, this is the way where things are. This is a little of their data flow. And what we're looking to do is use one of our previous data quality rubrics to assess what the quality of data is that they're providing for pedestrian volume estimates. So we'll look at accuracy, completeness, things like accessibility, how easy it is to get the data for any application, whether it's travel demand modeling, safety analysis, whatever. We'll try to report out as best we can on all of these metrics. I don't have results yet. They'll be coming hopefully here in the next few months. Would love to share out with groups that have any interest in this and let you know how it goes. So that's it for me on data fusion and the replica evaluation. I'm happy to take questions and wrap it up.
All right, thanks, Josh. Yeah, interesting presentation. Appreciated all the data sources and sharing of the results. Carol, I know we have about 5 minutes left. We're running short on time, as we knew we would. So probably not much time for Q&A for Josh at this point. Is there? I mean, I guess if folks have questions, they could always put it in the chat, and Josh can address those as well. What do you think, Carol?
Yeah, that would be a good use of chat.
Okay. These meetings are recorded, and so if you want to go back and look at the chat and look at the questions, that is available on the recording as well. Before we get into the announcements, I just want to thank all the presenters today for all your work in really taking data and your analysis and your results and bringing them to our forum and communicating them well, I thought, and just taking the time to share your work with our group. And answering the questions that were thrown at you as well. So appreciate that to all the speakers today. Moving forward with announcements, as we like to do here at the end, just talk about upcoming conferences that are that might be of interest to this group. It looks like there's a PSU workshop coming up in next month. Otherwise, if you have some travel budget and want to leave Oregon, I don't know why you would in the fall. This is the best time of the year in my mind to be here, but you could go to Irvine, California, or Denver and check out some conferences there. And then, of course, in the winter is the annual TRB meeting. Next slide, Carol. Topics that we looked ahead. I mentioned earlier that we try to do 4 meetings a year, quarterly. Our next one will be late October or early November, where we'll have kind of a vision eval theme, some applications, folks using it, as well as just a general overview if folks aren't familiar with the vision eval product, and just kind of give a general overview on that. And then late fall, just beyond this vision eval meeting, we'll look at some performance measures, regional mobility policy work that ODOT and Metro has done. So we'll be talking about that. And then per usual, every January we get together post DRB and just kind of share some interesting topics and different themes that we kind of take away from the annual meeting in the form of a brown bag typically at PSU. So again, future suggestions, lightning talks, we'd love to hear from you. The email is there, as well as the website for any past meetings or looking ahead at future themed meetings as well, OregonModels.org. With that, again, thanks everybody for coming today. We had a good turnout, and special thanks to all the presenters as well. Thanks everybody. And we'll see you in the fall.